involved in computing, being a lecturer in civil engineering. And so we've been going for 27 years. We started off under a company called SSP, then moved to another company which had a few problems, and then we became known as Mars System under someone else, and he sort of ran it into the ground, and we joined with Helifix in 2008. Had 4 good years with them, but they were taken over by a large conglomeration who didn't want to get involved in contracting. So we then joined with David Kitching with Stress UK, and we've been with Stress UK ever since. And we've done over 300 bridges. So the system has been very successful. We have no idea what that quote means, but anyway, it's a quote, masonry bridges. But and because I've added a few things to this presentation, I'm just going to run through. I'm not going to read everything, but we're very much believing in sustainability, and this has to be the most sustainable way of upgrading bridges that's possible. And masonry bridges themselves are the most sustainable structures that are.
Oh, Bob, I think you've just put yourself on mute.
Stopped. Is that better?
Yeah, yeah, we can hear you now. You just come off the presentation now.
Yeah, I have. Yeah, I'll go back. Hang on. How's that?
Yeah, brilliant. Let's come back up.
Yeah. Okay, and you can hear me.
yeah, can hear you.
Good. So part of our heritage, and say, you get paintings with masonry bridges in them, but you don't get many with concrete monstrosities, which are not very environmentally friendly in the first place. This was a bridge that we strengthened in 1997, and nothing's been done to it, and it still looks the same as when we started. So there's no deterioration in the Mars system, no deterioration in anything that we've done. It looks the same then as what it now is what it did then. So the system, we use inert materials, stainless steel embedded in inert materials, so it should last the lifetime of the bridge. In order to mess around with masonry bridges, you really got to understand them, how they were built, etc. Sorry, I've taken my pointer away. Initially they're built on centering. This is centering. This is actually a reconstruction of a bridge at the beginning of the century, so that's why they're dressed like that. But you can see all their hard hats, and they enjoyed their work. But this reconstruction of a bridge, but you can see it's built on centering. The arch is built from each side, etc. And then you put the keystone in the middle to hold it all together. In this case, they built spandrel walls as well. So when you remove the centering, the arch sinks and it all goes into compression. The barrel goes into compression, and then it can take load, etc. So it's all in compression as soon as it's built. Early arches were designed, but most of them weren't really. There's all sorts of early formula for rules of thumb for building bridges. A number of them were just built according to one of these rules of thumb. So you can't really say they were designed, but so we get to the construction of them. You build it a layer at a time, but you build your brickwork around this is roll-up construction. You build your brickwork around the centering. You remove the centering. The brickwork sinks, and you get compression in each ring. Now each ring is a different length. different shape, so it's a different stiffness. So you're going to get different. It's going to attract different forces. So you can get ring separation as soon as the bridge, because they're going to move differently, different lengths. You could get ring separation as soon as it's built. And if you build your spandrel walls at the same time as we had with that one there, the barrel can sink relatively to the spandrel walls because they're a stiff vertical plane. So you could get spandrel wall separation from the very beginning. This is a cross section of a bridge, and it's really a masonry bridge is really a system of competing elements. You've got the stiff vertical plane with the spandrel walls and the parapet walls there, which is not very stable in the lateral direction, but very stable in the vertical direction. Then you've got your barrel, which is here, which is flexible in the horizontal direction. So it's moving, so it's not stiff in that plane. So you very often get a crack between the two because they're trying to move in different ways. And depending on the flexibility of the spandrel wall, etc., and the amount of fill. So the fill is trying to push the spandrel walls out, or the parapet walls out, and the barrel is trying to move in that direction. And masonry bridges all move. Everybody thinks they're static structures, but they're not. There's quite a bit of movement in them sometimes. And so... Sorry? Is that a question, or was that... No? Someone had the sound on, I take it. So
apologies. I'll mute my mic. Apologies for that. Sorry.
So this is the crack that you normally get between the barrel and the spandrel walls. And if you think it's not moving, paste a piece of paper across and it'll start to crack. This is a detail that because we come across all sorts of assessments, etc. This is a detail we've seen someone trying to pin that crack. Well, it's a hiding to nothing because it'll just move to the side of the pins. We had a discussion at the last CPD thing about pinning, combining pinning and masonry. I mean, I'm not totally against pinning. I'm not a huge fan because it depends on the nature of the crack and what's causing the crack. Very often the crack will just move to the side of the pinning, and depends how much movement there is. So you really need to know the cause of the crack before you do any repairs or anything like that. Different strengthening methods. Dave covered this the last time, but I'm going to do it this time. You can have overslabbing. This is actually a very old note that I used to do with the students. So it can be filled with, you can put concrete around the barrel. To take the load, you have to strip all the fill off. You can put a slab across the top. I've seen people recommending steel beams going across the top, but all that acts as a seesaw around the crown, and you get cracking in the road surface. And also, if this is full of fill, you get lateral support, and it also takes away the lateral pressure from the spandrel walls, but it very often just cracks up in here. I'll show you one that we've done there. So overslabbing involves closing the road, deep excavations, maybe supporting the arch barrel. That's one that we were called in to put the Mars system in, but they'd taken the fill off before we got there. And I'll come back to that because that's one of my case studies. But services, again, if the fibre optics particularly, it can be about £1 million to divert, so it's quite costly. And this is one where they overslabbed it, but we didn't know what was in the slab. We didn't know the reinforcement. It was a reinforced slab, and it was acting as a seesaw across the crown of the bridge, so you're getting cracking in the road surface. not such a good idea. Relieving arches, again, putting in relieving arches with sprayed concrete or whatever. This is one that was done in Wales that we had a look at, and say it adds unwanted weight to the structure, possessions underneath, reduces the elevational area, so you get flooding. And if it's a brick barrel, I mean, I haven't seen it myself, but I've been told that the bricks can turn into mush because it's an impermeable barrier and the water stays there. And we took away the relieving arches underneath, put in the marsh system, and this particular bridge hasn't flooded since, as far as we know. So the marsh system doesn't reduce the elevational area, but we'll come on to describing the marsh system later. Mini piles, it's called the syntax system really, but that just strengthens a particular location, but the location of the critical axle depends on the number of axles, depends on the shape of the arch, number of fill, etc. So it only strengthens a particular arch, and you strengthens one location and you lose your natural arch flexibility. Can permanently damage the arch barrel. We'll come back to that because I'll show you a slide. And encourages ring separation, etc. It requires a road closure, and you need to know exactly where the services are when you're doing it. And if we've come across a number that have been strengthened like this, and we refuse to touch them because it doesn't fit in with our software because the response of the arch has been completely changed, so it doesn't act as a masonry bridge anymore. This is another pinning. I should say at the start that I really don't believe in putting metal into masonry bridges. Our metal is in a flexible substrate, so it moves with the bridge. If you have as the bridge moves, if you have a solid piece of metal in there, a solid anchor or whatever, you get micro cracking around it, and so in this case a number of them dropped out, and pinning like that doesn't stop cracking, etc. So you still get cracking. So yeah, this hasn't come off yet, but the idea was that we take all these pins out and put in the marsh system to make it more effective. This is another bit of a disaster really. Anchors were put into this bridge and they really just made matters worse. There's a crack there. The anchors were put in and cracks there. It was anchored like that. That was the position of the anchors. And what happened was that these cracks here, because this is now not moving, cracking, these cracks started opening up, and these cracks were moving daily. And it's going to be very difficult to resurrect that bridge. I mean, there's nothing we could do about it because the anchors were in there. But getting onto the mast system, this is the mast system. We put it in from underneath the bridge, so we don't touch services, we don't touch traffic. Traffic can still use the bridge while we're working. And we have called them dowel bars there. We call them radio pins as well, but they do dowel the rings together. And we have transverse bars, and that's so it all goes in underneath the bridge. And this is the system in place. This was the one I showed you earlier, but we have a MAR system. We put in radio pins because if we just put them in on the bottom ring, that bottom ring would stiffen and it would attract all the force, and that would move separately, and you could get buckling if you don't put in your pins in order to tie it back into the ring, into the bridge, into the barrel, and stop the rings moving between each other. So you need to have your dowels to stop ring separation and stop the bottom ring buckling. So we tie in the spandrel walls as well, so that we put in an inclined bar to stop it rotating anyway, and we hold them together. So we're holding the sides of the bridge together as well. So these transverse bars tend to be in tension, and the circumferential bars are stop the bending. It's like reinforced concrete, really. Skew barrels. These run along the brick joints. Skew barrels try to span perpendicularly, and you get planar weakness in a skew barrel. So what we do is we tie the planar weakness in back to the rest of the barrel, so the whole thing is acting as a proper barrel. This is one that's failed along the planar weakness. Don't know what I can do about that, but it's good. So the start of it all was this bridge in Chertsey. I used to work for Freeman Fox, and one of my colleagues was one of the ones with Brian Boughton who set up a company called SSP in a place called Sidcup, which is where I lived. And he invited me to come along and join the company because I was still full-time lecturing at the university. And I came along, and I was given this bridge to analyse as part of the Bridge Guard operation back in 1984, 85. Nobody had published anything on actually assessing masonry bridges, so I went back to basics. Professor Pippard's work. I tried Heyman, but Heyman didn't actually give me the answers I wanted from a practicing engineering point of view. But old Professor Pippard, I think he was a bit of a genius. He actually sussed out how this should work, and so this was all iterative. So I thought, I'm going to write a computer program to analyze this. It took me about 2 years, sometimes working all through the night trying to get the computer program written. As soon as it was done, Surrey County Council came along and said, actually, that's really useful, and can we buy a copy? So I had to make it foolproof, so that's how the program ASARC started. This is quite an interesting bridge because from a contractual point of view, because the contractor was asked to build it from, I think it was Mr. Payne, was a designer. Contractor was asked to build it from embankment to embankment, but there's nothing in the contract that said, you've got to join up with the existing road. So it was a big step onto the bridge when it was finished. So they had to pay extra to build another arch and take the bridge back down to the road. So it shows the importance of getting your contract right. This was the program ASARC that we came up with, way back in the day. Masonry arches, usually brick arches, fail with a 4-pin mechanism, sometimes 5, depending on the shape. These were a series of bridges that were tested by Transport Research Laboratory. This one failed as a mechanism failure. Rubble bridges usually fail in compression failure, because the rubble tends to be, it's the mortar that tends to take the load in rubble bridges. Different bridges you get, you can get, if I go back, this is normal roll-out construction, but you can get bonded barrels, you get roll-up construction, you can get ashlar barrels, you can get random rubble barrels, you get rubble barrels. They're all treated the same by codes of practice, and they do behave differently. So it'd be nice if someone would do a bit of research to see the difference in the modes of behavior of the different types of barrel. I've done a number of finite element models in my day. We only had linear finite element models. So the way I treated them was, you get a bit that's overstressed, you take out that part of the element or those elements and then rerun it until you get equilibrium. and that gives you a sort of non-linear approximation. So I've done over about 90 to 100 finite element models of different arches and different conditions, and you can see the hinges starting to appear as you increase the load. As far as the MAR system is concerned, when we add a load to a bridge for the mechanism failure, say, you add your load and increase the load, and you start to get a hinge away from the design load. As you increase the load further, you get another hinge at D. As you increase the load even further, a hinge occurs at B. As you increase the load even further, you get a hinge at A. Problem is, you don't know where these hinges are going to occur. B can be anywhere up here, A can be anywhere up there, depending on the shape of the barrel and the thickness of the barrel, etc., and the number of axles and the direction of the bogey, etc. So what we do is we strengthen the barrel. We put our reinforcement in so that the barrel is strengthened where a possible hinge can be, and we put in our pins as well. Now, this circumferential steel really is only effective in this part of the barrel, because that's the main location of the initial hinge. If you stop the initial hinge from occurring, then you delay the other hinges and you increase the capacity of the barrel. And the rest of the part of the circumferential reinforcement is just anchorage. We anchor it. And that's the MAR system in place. These are heli bars, but sometimes we use solid bars as well. These are nice and easy to bend, etc. So they're nice. And our MARFlex structure adhesive, designed specifically for this job. It's going to be thixotropic so that when you're putting it in over your head, it doesn't drop out. But it's essentially the same material that's been used in bridge expansion joints for say 100 years, maybe that's a slight exaggeration, a bit of an exaggeration, but they've been used in bridge expansion joints for a long time. And they're salt proof because stainless steel, we use stainless steel there, and you get a lot of salt water coming through masonry barrels, salt water attack stainless steel, so we protect it. This protects it against salt water attack, and so that's our stainless steel. So it's protected against rubbing against the masonry, because again, if you rub off the chromium oxide layer of the stainless steel, then it'll be same as normal steel. It does repair itself, but it's really important. We've got a system, trade secret if you like, of being able to put our bars in right in the middle of the slot. We cut the 12mm slot to put the 6mm bars, but we've got to make sure we've got the same thickness either side, because the adhesion to the bars, I mean, the MARFlex is flexible, and as I said there, for the sake of argument, the limit of flexibility of the MARFlex is 0.1mm per millimeter thick of cover, which is about right. Actually, I think it's about 1.14mm, but this is easy to comprehend. If you got a thickness of cover of 3mm, the limit of movement until the MARFlex completely takes the weight of takes the force of the bar would be about 0.3mm. So if you had 0.1mm there and 0.4mm there, 0.5mm there, this would take all the load initially, and this would take 0.5mm to fully engage. This only takes 0.1mm to fully engage, so this could actually break off. So you've got to make sure your bars are in the middle of the slot, otherwise it just doesn't work. So the 3mm cover is just sufficient to give us the movement that we want, limit the movement that we want, and protect the bar against corrosion from the salt water. I mean, this is a very simplified sketch. OVARP and partners tested our ASAP program, and they said it was the most accurate one of all the programs that they tested. This is way back in 1999, and the standard deviation against the bridges that were tested by TRL was way below everybody else's. So because I take everything into account, the program does. We tested the MAR system at Transport Research Laboratory, and part of a link program with other companies. And so the initial arch was one that was built 5-meter span, which is pretty common in real life, 3 rings of brickwork, and with sand between the rings just to simulate ring separation. And that was tested, the initial, and this is the MAR system tested. And so the initial bridge, they tested it to failure, but not to destruction. And it took 200 kilonewtons. We'd assessed it would take 190, and we assessed it that would be equivalent to a 7.5 ton weight restriction for that particular span and that particular bridge. We jacked it back into shape after the test to failure, and just put in the bottom ring of reinforcement just to see what that did, and it increased the capacity by about 30%. So actually it did work, but there is a danger, because I've done a number of tests in the laboratory at the university. There is a danger that it would buckle because it's just taking all the load. So that's just a particular case where it worked. We then put in, rebuilt the arch, put in radio pins, and tested it, and it just deformed slowly, because the other bridges, other arches that we tested to destruction, or TRL tested to destruction, effectively just explode. The bricks go everywhere once you get failure. In this case, it was a very controlled failure, and the jack went to its limit, so it couldn't go any further. So they had to take the load off, extend the jack, and then push it back down to failure. And it just came down onto the ground. This part remained intact, and this part remained intact, and it just moved slowly down the ground under the load. So it makes the masonry bridge very, very safe. For the test, we invited about 60 odd bridge engineers. There weren't odd bridge engineers. There were 60 bridge engineers who came to witness it. So we couldn't fiddle anything. I predicted, using the Masters program, which was just an extension, a simple extension of the ASAP program, I predicted it would fail at 349 before the test came along. It actually failed at 345, but my excuse is that it was weakened by extending the jack. So we're very happy with that result. But we only put in enough reinforcement to take it up to 40 tons. We didn't put in any more. If we put in more, we could have got more load. But there is a limit to how much reinforcement you can put in a barrel, because you don't want to over reinforce it, because then it's like reinforced concrete, it would fail in compression, and you wouldn't want that. So that was the testing. This was the one that Helifix tested, and it was didn't work. That's why we went with Helifix afterwards, and Helifix took over the MAR system. And so when Helifix strengthen bars, they use the MAR system. One we're talking about these mini piles. This, you can see the whole of the bottom ring fell away, so they can encourage ring separation, etc. in the test. So that was the other system. The MAR system doesn't change the stiffness of the barrel by very much. You can see from this is the unreinforced, and so the shape of the deflected form is very similar. It's just that the MAR system, this is where they change the jack, and so the MAR system gives you more strength and slightly less flexibility, but that's it doesn't essentially change the response of the masonry bridge, because it's small diameter bars in a flexible substrate. This is me looking very happy. We tested all my master's degree students, got a masonry bridge to test different types, different amounts of steel, different types of fill, different types of masonry, different shapes, etc. And it was in a glass box. So with a glass box, you can plot the original shape of the barrel, and then you can see exactly for yourself how it displaces under load. So we did loads of those over the years. We also tested masonry bridges. This is actually down in Ramsgate. We use a Kent weighbridge testing vehicle and the Surrey weighbridge testing vehicle because we know exactly what the axle loads are on these vehicles. So you can remove the cast iron weights to get the load that you want on the various different axles. So we can go from tear on the on the lorry up to only take it to 1.25 times the design load for the bridge, or the design strength of the bridge. So you can do static tests, and then you can do dynamic tests to see the effect of impact, etc. So that was and we used vibrating wire gauges under the arch to look at the load distribution, and actually we found that the codes were quite sensible. We got much the same response as you do in the codes. So the dispersion rules in the codes actually make a bit of sense. The very first bridge we strengthened was in Rochdale, 1997, and after we strengthened it, in order to make sure that it was all working, because it was the first bridge we'd ever done, TRL load tested it and gave us the answer that we wanted. So everybody was very happy. The claim to fame is that we appeared on the One Show way back in 2010. They brought in Dick Strawbridge, who is doing up his chateau in France at the moment. He had the biggest moustache in show business, partly. But the county bridge engineer for Gloucester, she's in the background there, got the one show down to demonstrate how the mast system works. And this is Dick Strawbridge. This is Fred from Helifix, and the handsome one is that's me posing next to them. So that's the mast system. Look at some case studies now. This is one we did in Sheffield in 2017. It was built in 3 different sections. It was the original bridge, then another section was other 2 sections were added afterwards. In Sheffield, and so it was erected in the 1730s, and then it was widened in 1796, fairly soon afterwards. So you can see probably they would put the centering up around the same profile as the existing bridge when they were building this section, say, and this section. But then when they take the centering away, it drops. So maybe they weren't aware of that. So you got 3 different sections of bridge. And we'll look at how we apply the loading to these. But this bridge here, they wanted to knock it down and build a concrete monstrosity, which is not environmentally friendly. And the locals said, no, we like our bridge. We like masonry bridges. And so Sheffield Council brought us in and to avoid knocking the bridge down. But this was, as I showed you earlier, they'd already removed the fill from the bridge, but they couldn't get the load with just putting fill, lead mixed concrete over it. So we were called in to do some strengthening as well. You can see the backing is actually in good condition here. It's not good to rely on the backing because we normally take a core through the backing just to see what it's like, because very often the backing shifts, and quite often in multi-span arches, etc., where in the code it says take it as a solid part of the structure, but very often it isn't. So you need to be very careful if you rely on backing. But the point of this slide really is here. If you wanted to know the barrel thickness, if you took a core through here, you get a much thicker barrel thickness than if you took a core through here, and it's just next to each other. So you have to be very careful about when you're taking the barrel thickness. You take a number of cores at least to and get the minimum core to get you your barrel thickness, because it can vary. I mean, it all looks very nice from underneath, under the intrados, but over the top it can be pretty rough. As I said, I don't like slabs over a bridge because that concentrates the load at the crown. There's no dispersion. The load, vehicle load there, comes straight down onto the bridge. This will sort of tend to lift up, and there's no dispersion, so it goes straight onto the barrel. Not a good idea. And if you got a number of axles there, it puts the whole load on there. I mean, this slab is contoured to the bridge, which is a good thing, but it does concentrate the load on the crown. And again, you can see fill is very variable. We see all sorts of things in fill, so you can see the old spandrel wall for the original bridge there. You can't be too accurate with, I know in laboratories they know exactly what the fill properties, but in real life it varies a lot. This is us installing the mast system. This is a floating pontoon we put in place. Say the approximate cost of those days, the mast system was 70k, but all the prelims, etc., and access for this was particularly expensive. Takes the price up to about 150,000, and it took about 6 weeks for a 5-man team to do the job from start to finish. So we put floating pontoons in there. This is a pontoon in the bridge. This is the access, so you can see it's expensive to get to the bridge and keep the public out, etc. So that's our work platform. Then we cut the slots. I think there's some bars in those slots, but they haven't been Marflex yet. And that's the completed installation. We didn't need to do this one. This was strong enough, but the middle one, the original one, needed more reinforcement than that. We always just put the minimum in, and minimum we can, and that's the bridge finished. So it's very difficult to spot the mast system in the bridge. This was the design of the bridge. You can see midspan, there's quite a lot of steel. There's just minimum steel in that part, and we didn't need any in that part. And that's minimum steel. Is just single heli bars at 400 centres. This is another one, South Wales, badly damaged by a flood, deformed, etc. So what we did was we jacked it back up into position, as we've done in that bridge in the laboratory test, and put the mast system in. In order to jack it up, we had to remove the fill, which is never a good idea. But there's a big lump of concrete there, and that's what was causing the bulge. And so again, it's always amazing. People used to use them as skips, I think, when they're putting in all sorts of rubbish over the arch barrel. Again, not pretty, a slate sort of bridge, but it saved the bridge, and it's away in a remote part of Wales, so that saved the cost of a new bridge. And this is one talking about concrete liners. This is one in the middle of Birmingham. It was actually 3 bridges in a row. There's a metal bridge at the far side which you can't see, but the main carriageway went over this bridge, and they strengthened it using concrete liners, which requires separate foundations. They had to narrow the canal, and it was an expensive job. They're then building a metro, a metro in Birmingham, and they needed to strengthen this bridge. So we came along. Didn't need to make the canal any narrower. We put our system in, and nobody notices it, because I had a friend who sails up and down here regularly, and they asked him to take pictures of this, and he remembered this part, but he didn't notice this. So that's our mast system. So that's the difference between the mast system and putting in it's so much cheaper and much less inconvenient. So that was our mast system in there. The bridge was a strange shape. That was the shape of the bridge. That was our analytical model. So that was a profile of the barrel, and in order just to confirm that, we dug trenches above the barrel, and that confirmed these steps here. There's another one we did. This is my claim to fame in that I improved on Brunel's work, this was on Great Western Railway. We did this in conjunction with Network Rail, Arcadis and Amco Griffiths, and I published a paper on this at the last one of the bridge conferences. But this was carrying some huge aggregate trucks, and it was deflecting by about 10 millimeters. It was quite frightening, so we this was Brunel's design. Very little lateral support really for the barrel, this is a bridge like this acts as a hard spot in the embankment, so the embankment sinks either side of the bridge, but you've got your hard spot here where you don't get sinking. And this is my local railway station at Bexley. I noticed this. There's a similar structure goes under the bridge, and you can see how the platform has sunk either side of the tunnel. It goes under the station at this part. So a good way of getting a feel for a bridge. That's me. I didn't realise I was quite so bald as that until our MD took my picture. Preferred the back of my head to the front of my head, but just holding a wooden pole up to the bridge, and as the train, I mean, I'd like to have got a picture of the train going over, but as the train goes over, you can feel how the bridge responds. You can get the response of the bridge very simply, and it was deflecting by about 10 millimeters. The bridge wasn't elliptical as it looked. It's near the Maidenhead Bridge, but it wasn't elliptical. It was three-ringed arch, so which is slightly easier to build because it's just circles, so that was the arch. In order to give you lateral stability, we used the Reforce system, which our sister company Stress, well, it's our parent company now, company Stress provided, because they have a system of improving foundations. Normally this is vertical, and they pump exact amounts of material in. So, because the big problem here is we don't want to get grout into the ballast, because then they wouldn't be able to reballast the line. And so we have to, very controlled amount of material grout goes into this, and so that's our lateral putting in lateral support for the barrel, because elliptical barrels, 3-center barrels, etc., do rely on good lateral support. This is our system. Because the deflection was so great under the aggregate trains, and because we didn't want to close the railway while we were working, this was the only bridge to date. Well, we've done another bridge now with propping, another railway bridge, but this is the first time props were used. Now, we've used a 25mm neoprene pad on the top of each prop because you don't want to put hard spots in there. And our guys were able to work around the props and put in the mast system. So that's to stiffen it up, I used 8mm bars, twin 8mm bars, because we wanted to stiffen it up. Normally we don't want to do that, but in this case we did. And so that's the mast system in the under the 2 railway tracks. So again, 8mm, call them Betanox bars. Again, we get these from Helifix, so in our normal Marflex adhesive, but you need bigger slots for these bars. Now, after we put the propping in, we had a number of stations where we measured the deflection, and you can see with the props in place, so you got your rubber pads actually taking some of the deflection. We got 6mm deflection, which is still a lot. After we put in the reforce system supporting putting in backing into the arches, we reduced it to about 3.5mm. And then by putting in the mast system as well, it reduced it to 1.25mm, which is more than acceptable. So this is the engine going over, and these are the carriages. It was actually, and sorry, this is wrong one. Before we put the mast system in, the deflection actually standing under the trucks as they went over, it was actually behaving perfectly elastically. It went down 10mm and then back up to the original position under each, so it kept going up and down. So it was actually behaving elastically, which surprised me, because I always thought they were non-linear structures. But that's the mast system in the bridge, and that's the finished bridge. And so we completed the project on time, on budget. Didn't close the railway line. We still had these big trucks going over, so there's no interruption to railway services. And we uprated it from RA5 to RA10 to carry these big trucks. So we improved on Brunel's design, but I mean, Brunel only designed for very lightweight trains in his day, so there's no way he could have anticipated what was using the railway line today. It's another one we just finished. This is with Arcadis and Amco Griffin again, but Transport for Wales had the railway line. In this case, this was a railway line, and it was assessed at RA0 due to ring separation. It was over a disused canal, but they wanted to put another track over the bridge. It was just a single track. Originally, they wanted to put another track and increase the line speed from 25 miles per hour to 30 miles per hour, which doesn't seem an awful lot to me. And I thought they wanted to do more than that. So this was an interesting assessment, because the original barrel was 700mm. In the past, they must have removed all the fill, put in a brick layer around the top, brick layer there, and then replaced this with lean mix, and then put the ballast for the railway track on top. The assessment took into account this brick layer, and they said this thickness was 960 thick. So that was the original assessment. But if we go back to the original slides, we can see that when you remove the centering, when you're building a barrel, the barrel sinks and it all goes into compression. If you put a layer of bricks along over the top, the bricks are not in compression. They're not actually taking any load. So you can't count these bricks. They're just a waste of time, really. You can't count these bricks as part of the thickness of the barrel, because, as I say, they're not taking any load. So we could only take this 700mm as the thickness of the barrel. The original barrel, they downgraded it because of ring separation, but because we're putting our radial pins in, we counteract ring separation. We did institutionally grout the barrel as well, just to make it better. So this was just working out all the coordinates of the barrel, because you've got to be very accurate with your coordinates. And this is the mast system in the barrel. We had to recase the bottom ring quite substantially. Now, I'm very much against recasing bottom rings, because again, you're putting in unstressed bricks into a stressed ring. If you take bricks out, bricks are in stress, they're in compression. If you then replace them with bricks that are not in compression, and the compression is quite high. We've tried putting wedges in, but you can never get the strength of the original compression. So we anchored it back into the foundations. We anchored, this is the anchorage area of our bars, but because there's extensive recasing there, where we actually anchored into the apartments. So this was the condition of the bridge initially. It was actually selling all sorts of drugs underneath the bridge as well, and a lot of the voids in the bridge were used to contain needles. But this was our guys. This was the original bridge. It was in dreadful condition. So you can see the brickwork, and we had to recase quite a lot of this to replace it. And then and as we designed the bar system for was it RA6, and then they came along and said, actually, we're going to be putting a tamper across. Can you redesign it to accommodate a tamper at 5 miles an hour? And I think all bridges need to be designed to accommodate a tamper, because tamper vehicles are going to be going over all railway bridges. But we found out that we did have enough in there to accommodate tamper at 5 miles an hour. So this was the bridge. Again, we put in, it didn't really need the props in this case, because there were no heavy aggregate trains going over. But we upgraded it to RA6 at 30 miles an hour from RA0, and RA8 for the tamper vehicle at 5 miles an hour. And this was the finished bridge, and guys made a superb job of it. So this is if you remember what it looked like beforehand, and we come along, and this is the mast systems in there. And the chap we had in charge there put an awful lot of effort into repointing the mast system and making it look part of the bridge. So that's the finished mast installation. I think Legree made a really nice job of it. Another case study over the River Nene or whatever you call it, Handle Bridge in Northamptonshire. It was built in 1329, again destroyed, etc. And we ended up with 13 spans from 3.5 meters to 6.2 meters. Had been widened and widened again, etc. And when you widen a bridge, very often the original foundations are different to the new foundations. So very often they didn't bother very much with foundations in the early days. Then it was wooden piles, wooden raft foundations, etc. So you get all different foundations. So the different extensions of the bridge were behaving differently. So it had a 3-ton weight restriction on it originally before we came, and Northamptonshire County Council wanted 44 tons and SV 100 vehicles. So we came along to the bridge and started off 2020, it was floods. The whole bridge was flooded. So we couldn't start. Then as soon as we were able to get started, COVID came along. So we issued air-fed helmets to all our guys. We had very, very strict COVID regulations for working in COVID. Nobody could touch each other. Only one person could be in the canteen with their own knives and forks, etc. There was no cross-contamination between any of the guys. They all had separate vehicles to come in to work in, etc. This is a vacuum drill for putting in the radio pins. So we managed to work as pretty well as normal during the COVID. The bridge, as I say, was extended in using different locations. This was an original Gothic part, and fortunately this didn't need strengthening. This was the strongest part of the bridge compared to all the other bits that had been widened, and this was a finished article. When you're increasing the strength. This was the mast system, so you can see different mast systems. I like to keep it separate. We're actually, because we're putting in the mast system, we're putting in more into this section than we are in this section, because this is moving more. We're actually decreasing the relative movement between the two sections, because we're bringing this into the same stiffness as this. But when we're doing bridges like this, if you're increasing the capacity by such a lot, you really need to look at your foundations and the increase in the load in your foundations. And we looked at all the different spans, and we reckon that if you're under 15% increase, you're okay, because it's the foundations have been there for 100 years and they've consolidated the ground, etc. One span, the middle of third span, actually the increase in foundation pressure was 21%. But all we did there was say that you really need to, it's not that bad, and you really need to keep an eye on it for all principal inspections. So it's just a flag for the local authority. This was the finished bridge. Heritage is a grade 2 listed structure. The Heritage guys were absolutely delighted with the finish, and we work very closely with Heritage people. And again, you can see that, you can't really see that the mast system's in there, and it gives people confidence that the bridge has actually been looked at and been worked on and strengthened. This is another one we did, another beautiful bridge over the river. This was Thrapston Bridge, again another grade 2 listed bridge, and again it started off with 24 arches, but when we got there there's only 9 left, these 9 arches over the river. And so there's a video there showing, because one of our guys is a drone expert. This is our site compound and this is the bridge, and I'll just let the video play while I talk about the bridge. But the main navigation span was critical, and that seemed to be moving a lot, and it looked as though it was forming hinges when we looked at it. And so we called into the to see what the support was like, because it had been extended in the bridge, so as we were worried about the safety of this arch, so we closed the bridge while we were working on this span here. But and that's the span there that we're working on, and we had a motorized platform that we worked on, so that people were coming up here in narrowboats or whatever, we could just move this out of the way and let the boats through while we were working. But the deflection was quite considerable in this navigation span. But we got some brilliant guys that can make brickwork look like the original, but there's lots of cracking, etc. in the bridge. So say for doing that span, we closed the bridge, but then when we came to do the other spans, the bridge was perfect, was opened again. But when we're doing, not all spans needed strengthening, but the council were worried about ring separation. So again, we put in our shear pins. Sometimes we didn't put in the mast system, we just put in shear pins just to stop ring separation. So we calculated the number of pins that we needed to stop ring separation and put in that number. But normally with the mast system, we put them in the intersections of the main bars and the transverse bars, and there's always more than enough pins to stop ring separation. Talking about big bridges, but I love little bridges just as much. And this was a bridge in Calderdale that had been strengthened by, or supported, if you like, by putting in a wrought iron plate and concrete over the top, and it had been widened, but this had been in part of the bridge. They'd also put in these abutments, added abutments here, and narrowed the stream. So we came along and didn't like this because it was, for floodwaters, it was stopping floodwaters, but it was going to be too much, too expensive, and not cost effective really to remove these. So this was the underside of the bridge. This was the concrete support under that part of the bridge, but in this part, because there's very little fill over the top, it was being some of those wires were being punched out. So the idea was to replace, repair the back of where the those wires have been knocked out, and repair the back of that, and take out this concrete infill. The effect of these inserted abutments were to give a pivot point to the actual barrel, so as the load comes on here and this deflects, it comes out here, and it's not a good idea. So our solution was to tie the barrel back into these inserted abutments, and take the span. We took the span as this amount, just as a sort of nominal increase in span when we were calculating the mast system. And so we put the mast system, but we put it down the abutments as well, just to tie everything in. So that was the mast system in that bridge. It was a lovely idea. But this was the original bridge, 40 millimeters displacement of some of them, and we just pushed them back up into place. And grouted them in place, and then put the mast system in place. So this was the mess. This was when we took away this concrete support. This was in a real mess, and we managed to straighten it. The wrought iron was rusting anyway, and it was about to fall down. And this bridge is actually used. There was a plant next door to this bridge, and used by some quite heavy lorries. That's why you got your punching shear. This was finished bridge, and you can see there's no problem with floodwaters. It won't flood, and this is a mast system in the bridge. So we saved that little bridge, which I'm very pleased with. This is a bit out of sequence, but this was one we had a meeting in Chelmsford, and I remember we doing Chelmsford Viaduct way back in the year 2000. Went up to have a look at it. Exactly the same as what it was when we originally installed the system. Yeah, no deterioration whatsoever. When we're doing our design process, we normally get an order, we normally get drawings of the bridge, then we'll get an assessment report. So we see an awful lot of assessment reports by different companies. Some are really good, some are not so good. We normally do an inspection ourselves, just to confirm everything, and lots of photos. Sometimes I can't get to see the bridge, don't get to the bridge, so lots and lots of photos are really useful. This is bonded barrel construction in this particular bridge. This is in Essex, and the other side is roller construction. And so the bridge was extended and widened and built in two halves. And you can see the difference in the halves there. Someone had put heli bars across. They won't do any good whatsoever because they're no good in shear. Trying to get rid of the differential movement, which is a complete waste of time. But also photographs that I get, it's also really useful to see what traffic's using the bridge, and you can see there's some big lorries there using that bridge, so we know what's the usage. Then we do our AIP to technical approval, and the two codes that we tend to use, 458 and 454 for this is for authorized weight vehicles, and this is for special vehicles. We also use, it should be irrelevant, unreinforced masonry bridges, because we're putting reinforcement in them, CD 376, but there's a lot of useful information in that code, so we tend to refer to it, such as it suggests that you shouldn't use LM1 load models to the Euro codes. So those are the codes that we use. We design our reinforcement to Eurocode 6, and so they're used as well. Then we come up with a design report. This particular bridge, I use ASART to analyze the loading, and then MARSYS to design, to work out the moment of resistance that we require. But because this particular bridge was split in the middle, built in two halves, you have to be very careful with your effective width of your vehicle, because these are acting independently of each other. So if you've got a wheel load there, there's no extension to your effective width. The original assessment actually took the whole bridge as their effective width, which is just completely wrong. So we're able to get the worst position for AW vehicles. I don't know if this, no, it doesn't. That's good. For AW vehicles, the worst position there is just near the edge of this slab. There's the dispersed load coming out. For SV vehicles, again, you can just fit one in, as you saw from that lorry. You can just fit one in to this slab here. When looking at this slab again, the vehicle there, SV vehicle would be position the loads there. This would give the worst case for AW vehicles for this slab, and the worst case for SV vehicles for this slab here. So you've got to be very careful about where you position your vehicles in order to get your worst case loading. It's no good taking a vehicle in the middle of the SV vehicle in the middle of the road, because then you're not going to get your worst case. So that's the reinforcement for this bridge. So you can see that slab actually needed more than this slab. So we're equalizing the stiffness of the slabs, so there should be less relative movement between the two. But it's not a good idea to take reinforcement through from one to the other, because you're trying to constrain movement, and you don't want to do that with masonry bridges. This is, I don't know if I should show this, but this is supposed to be the longest bridge in the world. I don't know, masonry bridge. We thought it was in Turkey, and we supplied all the materials to Turkey with Helifix. We actually got it through Helifix. And then we discovered it was actually being done in Iran. We trained the guys in this country, so it was all a bit of a mystery. But the reason for showing this is that's them strengthening it. And they did an assessment of the different forms of trying to strengthen the bridge, looking at technical considerations, historic, etc. But they didn't look at environmental advantages. And again, we won on these criteria, but if they put in environmental criteria, we'd have won hands down. But this bridge has been, after the MARS system was installed, it's been monitored by academics ever since pretty well, and they've noticed that it's much better response to seismic activity than the original bridge, and much better response to dynamic loading. So that was that bridge. This is one we're working on. We're just starting. I'm going over there. This is in India, in the GOLDHAWK region, and we're starting in February next year. It's all been approved, and it's a beautiful bridge. This is in the GOLDHAWK region, as I said. It's a very flat arch, very flat bridge. There's no crack between the spandrel walls and the barrel, because the barrel is relatively thick, and the spandrel walls are very flexible, so you can get the movement in the bridge. It's also very lightly loaded because of traffic restrictions. But I think it's a beautiful bridge. I think it was designed by the local Maharaja, who is a civil engineer, but I'm not sure. But I'm going over to meet him anyway. And this is one that I'm really looking forward to. I've spent a very pleasant day on a little dinghy going around through the arches. We took 3D model of the arch of the bridge. It's a grade 1 listed structure, and strangely enough, there's only two parts of the arches, I should say, that we reckon need strengthening. We've assessed the rest, and they're all okay. So it's just out this big structure here, which I think looks fantastic. We only need to strengthen two of the arches, so nobody will notice the bar system. But say a grade 1 listed structure, and it's closed to traffic at the moment, which is a mistake because masonry bridges don't like to be closed to traffic because you need to keep the compression in the barrels. Yeah, it's a nice bridge. Should mention, as mentioned before, bridge infilling. It's a criminal activity as far as I'm concerned. You need to quarry your materials, transport in large trucks through villages, etc. Then you need a large plant to put this stuff in place, and you're using concrete, which is not very good, and your effect on the habitat is dreadful. And this is infilling bridges. Compare that to the Mars system. A Marflex actually was manufactured in Town and Wear. It's now manufactured in Swindon, and I was there yesterday actually at the factory. So it's actually we don't have the supply chain is very local in the UK. We only work from small van. We only need small vans because we don't use big equipment. We only use hand tools, which we hire from the local hire shop. So we're giving work to the local environment. We use local scaffolders as well, just to build simple platforms normally, or pontoons or whatever we need. And we don't need to, I mean, one of the worst things you can do when you're strengthening a bridge is to close it to traffic, because then detours take up a huge amount of energy. And again, you can see we make a superb job of the finish of the bridge. I mean, the filled in bridge tends to look like that, but you're always going to get a void underneath that you can't inspect, and it could deteriorate, and you could get the whole barrel failing over that void. But fortunately, that they had to remove the infill from this bridge and go back to the original. But the infilling reportedly was 123,000. The Mars system design was 4K. Mars installation was, we did a genuine price match, and to put in the Mars system to strengthen this bridge would only be 86K compared to infilling, which was 123K, and it was so much more environmentally friendly. But they now had to remove it at a cost of 400K. So what a waste of money. So the Mars system, just to conclude really, we won the Millennium Award for Innovation. Brian and I had to go up to the Dome to get presented by Tony Blair, who was the Prime Minister at the time. And we were described on the Spiral of Innovation as an example of the very best in British ingenuity. And our design is our software. OVARP said it was the best fit to test data of any other method that was available. System doesn't add weight to the structure, doesn't reduce the elevational area, and doesn't significantly alter the appearance of the structure. I think it makes it look better actually, but I'm biased. And doesn't normally require a road closure. Sometimes we have to put in a width restriction just to stop big lorries while we're putting in the stuff, and it only takes about 2 or 3 weeks to put in the material. So further advantage of the Mars system, it utilizes the inherent strength of the barrel. So we don't have to replace the barrel or do anything like that. So it's a minimum amount of additional material that we add to the structure. It preserves the inherent flexibility of masonry arches and improves the structural behavior and the elastic response of an arch, but they still behave in exactly the same way. We don't need alterations to statutory undertakings. This, you can't really see this, but this is the arch barrel here, and that's the roadway. It's one of the busiest junctions in Britain, near Bury in Lancashire, and there's loads of services in there. And the Mars system really was the only system they could use. So we strengthened that while road was working, and again, been no problem. That was a long time ago. Been no problems with it. We preserve diversity because little fish can swim around our scaffolding or under our pontoon or whatever, and we don't interfere with fauna and so other alternatives. Environmentally cheaper and financially cheaper as well. Easily inspected and repaired. You don't need to. As you can see, there's no deterioration in the material as we go through the years. But you can, when you look at it, you can see the spacing. If you don't have any records, if the records get lost, you can always take away some of the bars, and you can see the number of bars that we used, the size of the bars, and you can actually recalculate the strength of the bridge in, say, 50 years' time or 100 years' time. If you've lost all the documentation. So, because we've an awful lot of bridges we look at, documentation has been lost as local authorities move and merge and etc. etc. Cures ring separation. I mean, a number of academics have said this is the principal mode of failure. Maybe in a laboratory it is. I'm not convinced, but yeah, it's at least we cure it anyway. There's no road or rail closures. We can keep things working. Very rarely, as you saw in that other one in viaduct over the River Nene, we did close one span as we were doing it because we felt it was a bit dangerous, but that's very, very rare. We're using that durable materials that so they don't deteriorate. Operations can be planned sequentially to minimise inconvenience to users. This was a railway bridge we did. We only had a possession for a few hours on a Saturday night, every Saturday night, so we had to come back every Saturday night and do a little bit more and a little bit more. I think it took about 10 weeks or something like that to do that bridge, but it's still there. And really fundamentally, most importantly, it is the most environmentally friendly method of masonry arch rehabilitation. So that's how we work it. So there's YouTube presentations that you can get on our website explain the system more. But thank you ever so much for your patience. It's gone a bit quicker than I expected, to be honest. But any questions, I'm more than happy to try to answer them. We had a good discussion the last time on stitching in conjunction with the mast system, but that's us. And part two, Dave Kitching will be We'll be presenting part two on the 21st of November at 12 o'clock. So look forward to seeing you there again, if possible. But anyway, that's me finished. If there's any questions.
Brilliant. Thanks very much, Bob. Guys, feel free to step in or put your questions in the chat or raise your hand, and I'll pass it over to you to ask any questions you've got to Bob off the back of that. So yeah, we'll have a few questions if anyone's got any. There's quite a few comments.
I've just had a very bad game of golf, so I'm not in a good mood. So played very badly.
No golf questions then?
No. Do I recognise any names?
If anyone does have any questions, guys, I appreciate it. Yeah, it's kind of come up to lunchtime, or if you've got other meetings to jump on, then feel free just to put them in this chat, and I can pass them over to Bob, and hopefully see a lot of you for part two. I will send out the invitation links to everyone who's attended today for part two over the course of the next few days, early next week, so you can dial in for that one. But yeah, if anyone would like the recording to this as well, then just let me know. And like I said, any questions, feel free to put them in here, and I will pass them over to Bob. But if there's no one,
I'll be involved in part two as well. So if anybody's got any questions on this, I'll be.
Yeah, no,
that's good.
Absolutely. But yeah,
I think there's no questions, to be honest. It's easier.
There's lots of comments in here with thanks to you, Bob. So yeah, and people who've enjoyed the session. So great, and yeah, thank you to everyone who's attended. So if there's no questions, I will. Oh, do we have one? We might have one. No, we don't. I thought it was.
Yeah, I've got some slide coming up.
Yeah, like I said, guys, put them in this chat, and we've got access to them if you've got any questions. But if not, I will. Yeah, thank you all for attending, and end the record now. And thanks very much to Bob as well.
Okay, pleasure.
Brilliant.
Okay, all right.
Thank you very much, guys. Take care.
Bye.
Thank you, everyone.